Okay, today what we're looking at is what's called matching and allocation. So we're going to match up things and then allocate jobs or tasks or whatever. So what we do for these is we use things called bipartite graphs. Alright, so what a bipartite graph does is it joins two groups. So this graph joins two groups, and the two groups not necessarily related but somehow connected. So the groups, we set them up with their vertices one under the other. So the groups are set out with their vertices under each other. Alright, so let's fix that up under each other. So here's an example bipartite graph. So you've got some people over here on the left, and you've got some animals over on the right. So there could be some sort of connection, maybe. I don't know which animals they like or something like that. The other thing is that we could have could be directed. Alright, so that previous one wasn't directed, it just had no indication of which way that. Alright, so here's, a directed one, so we've got four people here, and we've got some instruments. So here we've got a directed graph, so line there, Helen to drums, indicates, that Helen can play the drum. Whereas, Ian, here, Ian's got an arrow to the bass and an arrow to the guitar, so Ian can play both of those. So, here it's the person plays the instrument, not the other way around. Alright, so our directed graph shows what's connected to what, or what does what. Now, we could also have a weighted graph. Alright, and so here I'm going to use an example. I'm going to follow this example through. So, for example, what we've got is, so we've got 4 employees. And 4 machines. And each employee can operate them all. All machines. But maybe their proficiency on each machine may be different, so that leads then, so it's then the weighting so the weight indicate the time each person takes to perform a task. Alright, so again, you get your bipartite graph like that, so person on one side, machine on the other, and you end up with something like this. So they can all do things. Now, you see a lot, I've started to fill in some stuff. So like Penny, for example, she can operate the spray task, but that's going to take 70 minutes. She can operate the folding machine, but it takes her 50 minutes to complete the task for the job. She can do the press, that takes 80 minutes. The cutter, that takes 20. And you can see even with that little bit here, it starts to get very, very confused. All right, very confusing. So because of that, what we do is we use a table instead. All right, so our table would be something like this. We would have our employee here, and we'd have our tasks across here, or our machines, I should say. Machine. All right, across the top. So, we've got Mark, Neil, Orianthe and Penny, and then we've got a cutter, a press, a folder, and a spray. All right, and then we'll have times in the table. So here's one prepared earlier. All right, so here's our table. So if we look at this one, this bit here, what that tells us that if Mark operates the cutter, he's going to take 30 minutes to complete that task. Oops. Alright, so there we are. So this here is what's called a cost matrix. Okay, and a cost matrix shows cost. Now cost, you need to again think broadly of what cost is. Cost could be time, could be money, alright, etc. Okay, and so in this particular one, as I already mentioned, there might be a particular job that needs to be done to manufacture a particular thing, and so we've got these people, and on this job, this is the time. If they do the particular task to making the whole thing, that's how long it's going to take them. Alright, so what we want to do is we want to find the shortest time. So to find the shortest time, we use a thing called the Hungarian Algorithm. So let's have a look at the Hungarian algorithm, and I'm going to use this table here, this example, to work through the Hungarian algorithm and see what the shortest time is to complete the job, the whole job, and also who does what in terms of that. All right, so let's go over the next page here for our Hungarian algorithm. I'm just going to... Okay, so here we are. So there's our things, step number 1. So for each row, we subtract the lowest value in the row from each in the row. All right, so let's have a look. So when we look at Mark's row, you can see that the lowest there is 30, so we take 30 from everything. All right, Neil, when you look at Neil, he's the lowest, and again, so we're taking 30 from everything. Alright, Orianthe, when we look at her, 30 as well, so we take 30 from everything. And then finally when we get to Penny, 20, so we take 20. Alright, so that's the first step. So when we do that, we end up with this. Okay, so this is what we end up with. And I'll try and take my photos a bit better next time. But this is what we end up with after we've taken those values from each of those rows. Alright, so we're up to step number 2 then. So in step number 2, we put lines through the columns and rows taking a 0. Alright, and the fewest possible lines. So once we've got a line through a 0, then you only need one line through the 0 at the moment. So put lines through. The columns or rows containing a 0. And we want the least number of what lines. Alright, so let's have a look. I'm going to do them in orange. So there'd be a number of different options, but we want the least number. So if I just went like this, that would work, but there's 4 there. Now, let's take those off. So what I do notice is in C, I've got 2. I can cut 2 across there. And I'll just go down that column and down that column. So there we've got 3 lines. Now, we know we've got 3 lines, but we've got 4 tasks. So from here, we need to have a look at what we might do to get 4 lines. So we've got to get 4 lines there all together in some way or other. So step number 3. And step number 3 is to look at the column without any lines there, and that's this one here. And what we do then, let me rub all of that out so that then I can write down what it is. Alright, so step 3. For the column without a 0, alright, we want to subtract the lowest number from each. Subtract lowest from each number. Number in that column. All right. So what we're going to do is in this column here, because 10 is the lowest, they're going to take 10 from everything. All right. So when we've taken 10 from everything, this is what we end up with. Alright, so there we are, and so I've just got in red there, that's what I've done. So I've taken 10 from everything, and now that's what I end up with. Alright, step 4, put lines through. Again, we're looking for the minimum number of lines. Step 4, oops, let's change back to black. Step 4, lines through zeros. And we're looking for the minimum number of lines, using as few as possible. Alright, so let's go some green lines this time. And I can get 2 if I go there. I can get 2 if I go there. And that leaves me with just one more down there. Alright, now I could have gone horizontally again to get that, but it doesn't really matter which way we go. Now we're looking for 4 lines because there's 4 tasks and we've only got 3. Alright, so let's have a look at what's going on here now with this one. So we need to know step number 5 here. Alright, so step number 5 is smallest uncovered value. So smallest uncovered value, well, when we look at the smallest uncovered value, it occurs twice, is 10. Now here's the next thing that you want to do. So what we want to do, we need to add that number, in this case 10, to the numbers covered, writing's bad today, covered by 2 lines. Alright, so that's these two. We're going to add to that. And the other thing we want to do, it's red for that, is we subtract from all uncovered. Alright, so we're going to add 10 here, add 10 there, and all uncovered we're going to take 10. Like so. Alright, and then when we have done that, it looks like this. Alright, so there it is. So the red there, that's what I've added and I've taken. And so step 6, whoops, let's go back to the black. So step 6 is to repeat for step 4. Alright, and step 4, remember, is the lines covering. Alright, so this time, let's have a look. Let's do our lines in green. So I can get lines through 3 if I go that way. I can get through 2 if I go that way. And now there's 2 others. And I could go horizontally or I could go vertically like that. But whatever way, in this case, we've got 4 lines, and 4 lines is what we're after because we've got 4 bits of information. So, what does that mean? Well, the key things that we're looking for here is the zeros. Alright, because this is completion time, alright? So let me get rid of those drawings. There we go. So the key thing here is the zeros. So the next step, step 7, is for us to transfer the information to a bipartite graph. All right, and the zeros are the key things. All right, because the zeros, using the Hungarian algorithm, we've narrowed it down to the best options for people. So, like Mark, for example, here he's got 3 zeros, so it doesn't actually matter whether he uses the cutter, the press, or the folder. The job's going to take the same. What you don't want him to do is using the sprayer, because he takes 30 minutes longer than the shortest person. All right, so when you get your bipartite graph of that, it will look something like this. All right, so here it is. So remember, I said there, all the zeros are what's connected. All right, so they're marked with those zeros. He can operate any one of those machines. All right, so that's step 7. The next thing was we make the allocation. Now, while we're making the allocation, the key things we look for, is there any people that are best doing one thing? Or is there any one particular thing that needs a person? So when we look at this here, when I start here at Penny, and then I'll look at Orianthe, because they've just got one line from each of them. So Penny, she needs to do the cutter. All right, that's what she's going to be quickest doing for the whole job. Orianthe, the best thing for her to be doing is operating the spray. All right, now Neil and Mark, so Neil could operate the folder or the press, either one of those. So Neil, folder or the press. And Mark, when we go to Mark, so he can operate the cutter, the press and the folder, but the cutter has to be done by Penny. So I'm not going to put that Mark could be doing the cutter. So he could do the folder or the press as well. Now, the fact that both Mark and Neil here have got the same things means that it doesn't matter which one of those people does that. It's interchangeable. The time will be the same. So step 9 then, the last step, is to figure out the minimum cost. In this case it's time. Cost, time from what they do. So we've got Penny, and she's operating the cutter. We've got Neil. Sorry, I'm going to go back with that one. Let's get rid of that. Cutter, Orianthe. The spray. I'm going to give Neil the press. Alright, doesn't matter whether you gave him the other one, because he and Mark are just as quick on both of those machines, and Mark's on the folder. Oops, I don't know why I put 30 there, up that, because Neil's on the press, not on the 30. and marks on the folder. Alright, how long do they take? Well, to find out how long they take, we need to go back to our original cost matrix. Alright, so we did the Hungarian to find out what's the best. Now we're going to go back to our original. So here's our original cost matrix. Alright, there's our original cost matrix. Now, we said that penny is going on the cutter. So penny's going on the cutter. So penny on the cutter takes 20 minutes. Alright. Oops. Orianthe's on the spray. So Orianthe on the spray there, 30 minutes. Neil's going on the press, so Neil on the press, 30 minutes. And finally, Mark, whoops, too many. Mark is on the folder, and Mark takes 50 minutes on the folder. So 50 minutes, oops, 50 minutes. And then we add all of that up, and when you add all of that up, you get 130 minutes. So the shortest time that whole job will take will be 130 minutes. Alright, so it takes a bit to get your head around that, the Hungarian algorithm. So here's some practice of that, and the practice of that is in exercise 15B.